Hello everyone, this is Dr. Vahid Aryadoost. I'm delighted to demonstrate how to do a repeated measures ANOVA using SPSS. This is the data set that I'm going to use. As you see, there are 4 repeated measures over time. The data is from Green and Salkind in this book using SPSS for Windows and Macintosh. 2014. However, I have just also taken the liberty to include a variable called gender. It's basically a fictitious variable which I added because I wanted to show you how to do repeated measures ANOVA with an independent variable as well. But I'm going to start showing you how to do a simple within subject rather than within and between subject analysis. So I'm going to open General Linear Model menu and move down to Repeated Measures. I'll click, and this window pops up, which reads Within Subject Factor Name. The within subject factor name is time, as you can see. So this is a factor and it's called time. How many levels of measurement do we have here? 4. Time 1, time 2, 3, and 4. So I'm going to input 4 and add it to the box below here. It's important to add it, otherwise when you move, otherwise you cannot even move to the second window. I think that's it, so I'll just click on Define and this window pops up. As you see, we have 4 within subject variables of time. That's the variable that we named it. And each of these time variables corresponds to each of these question mark variables. So these are pretty much like placeholders, and we have to move our variables to replace the placeholders. Time 1 to time 2 to time 3 and to time 4. So for this analysis, I'm not going to use gender. I'll use gender in the next video. For model, I have explained this before. I'm not going to change anything. And since I don't have any missing value, I'm going to maintain type 3 for the analysis. Type 3 for sum of squares. For contrasts, actually contrasts in this analysis provides us with measures that would indicate whether our analysis, our data are linear, are quadratic, or cubic. So I'm going to leave polynomial as is, and I'm not going to change it, and just click continue. For plots, as I have discussed kind of extensively in the ANOVA videos, it's always useful really to have a plot, although they don't really tell us much. But they just provide us with some visual representation. It's useful in the sense that that visual representation of the data can help us figure out what's going on just at one glance. So I'm going to move time to horizontal axis and add, and that's all I want to do. I don't want to get I don't want to include error bars because it makes the plot quite messy, in my opinion. Post hoc analysis, as you see, is not generated, and the reason is that we don't have any between subjects factor here. If I move gender, gender has 2 groups, we still do not get any post hoc analysis for it. You will see it here, and you can move it to the post hoc test 4. But then when you run the analysis, you'll get an error message to say that post hoc tests were not run for gender because it has 2 groups. So I just wanted to show you that post hoc analysis cannot be done when you have a within subjects variables design. EM means are always useful. We need to move both overall and time to display means for. We display means for, but we also need to compare the mean scores of these 4 variables over time and I prefer to have a Bonferroni correction because it's robust against the type 1 error. Continue. Now under save, I'm going to save standardized residuals, and I have explained this in a separate video. Please, if you have not watched that video, please take some time to watch it. But basically what we're doing here is to test one of the assumptions of ANOVA, which is the normality of residuals. So by doing this, we will be creating a new variable, and we will be testing whether that variable is normally distributed. The variable is a residual variable. And for options, we have a lot of options actually. Descriptive statistics are always useful. Estimates of effect size are necessary. I would check homogeneity tests if I had a between subject variable. Currently I don't have it, but I can still check it off, so you will see the kind of message that we will get later. So with these checks and assumption checking out of the way, we can start to get the results from SPSS. I'm going to click OK, and that's it. Like I said, homogeneity specification in the print subcommand will be ignored because there are no between subjects factors. So that's the kind of warning that you will get. But this is not an error message. It's just a warning that what we wanted to do cannot be performed because there is no between subjects factor. Okay, so very basic statistics are presented first. Within subjects factors, we know that there are 4 time measures. That's exactly what we got in the data set, as you see, time 1, time 2, time 3. I'm going to delete these because, well, this is the standardized residual that was saved, actually, because I have been doing this a few times, so it has been saved quite several times. So this is what we saved. Now there are 3 major tables here that need some serious attention. One is the multivariate tests, one is Mockley or Mochley's test of sphericity, and the other one is test of within subjects effects. So I have already done this analysis, and I have copied and pasted these 3 into a separate file here. I think it will be easier to look into the tables on this separate file. So I'm going to draw some tables and stuff. So the first thing that we need to look at is actually Mochley's or Mockley's test of sphericity. I have heard both ways of pronouncing the word. Anyway, what do we do with this? This is a test of equality of variances. From this perspective, it's somehow analogous to Levene's test of sphericity in ANOVA and t-tests. But to be more specific, it's a chi-square. Mochley's test of sphericity is a chi-square test. And sphericity itself is a condition where the variances of the differences between the groups are equal. And we want to figure out if this assumption is met or not. So one of the first things that we need to look at is the significance level, the significance value of the test. Pretty much like Levene's test of homogeneity of variances. If the significance value is less than 0.05, then the assumption of sphericity is violated. That's the variances between the groups. The differences, variances are the differences between all possible groups, all possible pairs, are not the same. So when they're not the same, there are at least two ways of looking at the results. The first way is really easy. Some people say even though this is violated, because ANOVA tests are robust and powerful. They don't you don't even need to take into considerations any corrections that is offered by epsilon tests. So whether or not sphericity is violated, that's fine. That's the first, I would call it the first school of thought. So people would say, just stick with multivariate tests. And I'll explain these multivariate tests in a second. But then a lot of people believe, and I think by people here, I simply mean statisticians and scholars who use this approach, believe that when the assumption of sphericity is violated, as indicated by the sig value, we need to make corrections for the degrees of freedom. There are three ways of making that correction, and these are called epsilons. One is Greenhouse-Geisser, one is Huynh-Feldt, and the other one is lower bound. Lower bound is very conservative, is the most conservative one, and perhaps the worst possible case. So we stick with these two statistics, Greenhouse-Geisser and Huynh-Feldt. These two. Between these two, the preference is given to Greenhouse-Geisser. So basically the idea is that most often, and I think my data is somehow an exception, but most often we see that these two are very close to each other. But if they're not, like the present case, we stick with what a Greenhouse-Geisser statistic, epsilon statistic, is. In this case, the rule of thumb is, I mean, there are two ways of doing it now. I'm gonna first demonstrate the way that is more common, and it's like this: if epsilon, especially Greenhouse-Geisser's epsilon, is smaller than 0.75, then move to the next table. That's between the test of within subject's effects. If epsilon is smaller, if this one is smaller than 0.75, then move to the second table and look into Greenhouse-Geisser's statistics. This is an F-test, as you can see from F. This is an F-test which corrects for the degrees of freedom. Because if sphericity is assumed, the degrees of freedom are 3, because we have 4 times, time 1, time 2, time 3, and 4. But then after correcting for the degrees of freedom, we will get another F, which, quite interestingly, in my analysis, is exactly the same across all tests of within subject effects. And that's, I think, something really cool. But we sometimes, or I should say oftentimes, see that the F statistics are different, and sometimes SIGs as a result are also different. So let me just reiterate what I said and then move on to this table here, to multivariate tests. The rule of thumb is after we make sure that Multi's test of sphericity is violated, we look at these two statistics, these two epsilon statistics, Greenhouse-Geisser and Huynh-Feldt. If they fall below 0.75, especially Greenhouse-Geisser, which you see this does not fall below 0.75. In this case, this does, and this is more conservative. Therefore, we stick with this because it will give us more confidence that type 1 error is not committed. So if this happens, then we go down to the test of within subject's effects, and we'll look at Greenhouse-Geisser, and we interpret it as our F-test, pretty much like how we interpret usual ANOVAs. So our test here indicates that there is a significant difference across time, between the measurements across time. But where that significant difference lies, we still don't know. We can find it out later. I'll show you in a minute. Now let's just pretend that this significance value was larger than 0.05. What would we do? Meaning that sphericity is not violated. What should we do? When sphericity is violated, so we look at the epsilon. When it's not violated, a lot of people stick with multivariate tests, and some people recommend that we just stick with sphericity assumed test. In my case, interestingly, the sig is quite, the same, because it indicates that there is a significant difference across time in the variables we're measuring. And similarly here, we see that there is a significant difference. Now, if you want to stick with the results of our multivariate tests, which I recommend, we should take into consideration that there is a difference between peelized trace and Wilks lambda with the rest, with Hotelling trace and Roy's largest root. These two are the most conservative, so let me just use the red color. Therefore, they're not recommended to be used or to be applied, although some people might say it's for this reason and that reason they're fine to be used. But peelized trace and Wilks lambda are most often used, especially in applied linguistics, where you see that people most often report their Wilks lambda test results. So let me show this to you. This result here, the one that I just highlighted for you, are usually reported in applied linguistics, although statisticians say that peelized trace are also robust, and perhaps even more robust and more powerful than Wilks lambda. So I leave it to you to decide, but in this case, as you see, the values are very close, the F values are the same, the significant values are the same, and the partial eta squared values are exactly the same too. And this applies to even the most stringent tests, or Hotelling trace and Roy's largest root. So, in conclusion, we have to look at sphericity. If it's violated, we go by the rules that I mentioned. We check geysers, Greenhouse-Geissers test first, and if it's below 0.75, as I said, we go to this table and check Greenhouse-Geisser, etc. And if it's not violated, I would recommend that you report multivariate tests. And an advantage that multivariate test provides us with is that in this analysis we have a higher partial eta squared value of 0.382, which is basically medium size. But if you stick with this, partial eta squared is between medium and weak. So I'm going back to the results. I have reviewed multivariate test results with you, Maltese test of sphericity, and test of within subjects effects. Now this is a test of contrasts, within subject contrast. What it basically is telling us is actually the shape of is the shape of our graph. The graph being this. As you see, there is a linear progression from time 1 all the way to time 4. So the best way to describe it is a linear model. Quadratic models, as you can see, the linear model, and let me just again highlight this so you will see what I mean. So linear model has a significance value of 0.002. A quadratic model is not significant, so our quadratic a quadratic graph would look like something like this. For example, time 1, time 2, and then time 3, times 3. Sorry, I need to do it again. That's not very quadratic. So something like this. This is the horizontal and vertical axes. Okay, so something like first a linear progression followed by, for example, a dip. This is what quadratic usually looks like if you have just a few time points. But then if you have more time points, it would look like this, and so on. So cubic is also different. Do we have to report this? I have never seen anyone reporting this, honestly, and it's up to you really if you want to report it. But it's useful because it gives you an idea about trends. Because it tells you if the trend is linear. So it's linear, meaning that with one rate of decrease, whatever our dependent variable is, it decreases from time 1 to time 2 to time 3 to time 4. I think that's somewhat useful, but I don't see how necessary it is to report it. So test of between subjects is also significant here, but it's well, we don't have between subject effects here because we didn't include gender. I'm not sure why it's estimated here, to be honest, but I don't think it's necessary anyway. What is important here is to look at the estimated marginal means. There were two means which we selected. One was the grand mean, or the overall mean, if you remember. The overall mean for all 3 or 4 variables which we looked at is estimated to be 64.065. That's the overall mean. Now, this overall mean is very useful because you can compare these means of time 1, against it. So as you see, the first two mean scores, time 1 and 2, are above or greater than the grand mean. But then suddenly time 3 and 4's mean scores drop. They drop below the grand mean of 64 something. That's just an observation. Now we can do pairwise comparisons, and I think this is an important way of looking at the differences between these time points. So I always do this, and let me just do it again. No. I transfer the data in pairwise comparison tables to Excel sheets because I think that's easier for me to interpret. What we're interested in the first place is to compare adjacent time points. Time 1 against time 2, then 2 against 3, 3 against 4. Hopefully we find significant differences between each two adjacent time points. If you don't find that, then I recommend that we start comparing time 1 with time 3 and time 2 with time 4. I like that. Or ultimately, if you do not find any significant differences, hopefully we'll find a significant difference between time 1 and time 4. So let's do one thing at a time. First of all, time 1 against 2. I'm going to like this. Just embolden. Okay, this is easier to see. Okay, I'm gonna compare these two. Okay. There is no significant difference between time 1 and time 2. I'm not really surprised to see this because look at the differences between the mean scores of time 1 and time 2. There's hardly any difference between them. And you can see that from the descriptive statistics, both are about 65. The difference is very negligible and small. So there is no difference here. Red for no difference. But now, since our first analysis, as I showed you, is not significant, let's move on to a farther place, an analysis between time 1 and time 3. The difference is time 1 and time 3 are significant. That's good news for us. And time 1 and time 4 also have a significant difference. What does this mean? It means moving from time 1 to 3, you see a significant difference. For example, if it was a treatment, there is a significant difference between people who enter the treatment at time 1 and their repeated measure at time 3 and the last measurement at time 4. That's probably good news for that intervention. Now, time 2 and 3, because we do it progressively, we don't compare time 2 against 1, but time 2 and 3, yes, there is a significant difference between them as well. So the difference, that this dip that you see that moves from time 2 to time 3 is statistically significant too. Just by visual inspection, you can really say that this is respectable. The dip from number 2 to number 3 is respectable, and luckily we have statistical significance for that. Now time 2 against time 3, time 2 against 4, time 2 against 4 is much more pronounced, and I would expect to see significance level below 0.05, which is actually like that. Now time 3 against time 4, 3 and 4 is not significant. So when you're moving from time 3 to time 4, although you see that there is a change, that change is not significant. Yeah, that change is not significant. Overall, from time 1 to time 4, there is a significant change. And that's, I think, one of the important findings for our analysis. So I think this is the same multivariate test table which I already discussed above. So I think that's all about this analysis. In the second half of this video, I'm going to discuss how to use gender in this repeated measures ANOVA test. Thank you for your attention. If you liked this video, please give it a like and subscribe to the channel. Have a good day.